Good morning. We're starting it today with Chapter 13, and we're going to go under Hybrid, plc.org, pick the Hybrid tag, go under Hybrid Text. With that, come down to Chapter 13 on Indexing and Batching Applications. This chapter is primarily a chapter on batching applications. We get into all kinds of areas of data storage and recipe storage and handling of data. So this is more of a general topic than just a batching, but we talk about it from the point of view of batching, and then we get into other areas as well. So as we look at this chapter, one of the main things we look at is, where did we come from? Well, Modicon was a innovator of programmable controller languages at the beginning, and they were the first in many ways to introduce some of the concepts that we now take for granted. But we knew that we needed to have a method for being able to index through a group of words and data words, and so they invented a way called table to register, register to table, and table to table. Table to register took a word from a table based on an indexer and put it into a storage location separate from the table. The register to table did the exact opposite. It took a single word and placed it into a table down the table based on an index. Table to table was a copy of a whole table to another table, either a word at a time or the whole table. So basically it allowed you to word by word move from one table to another table, or the whole table at once, which would be a copy command. Typically we would call a whole table blast would be a copy command. So we also talk about in this chapter about some of the earlier PLCs that Ellen Bradley had. And then we get into the Siemens processor as well. And we also look at weighing systems and different ways of weighing things. And we also look at the specification from ISA SP88. It's typically called SP88, but has other names as well, but the number 88 is there. Because about in 1988, people at ISA came out with a specification on batching. It was a very good specification, so if you ever wanted to go into writing of a batching program, you should look at that specification and review it. And we just go through then we talk about the specification as a way or a means of a checklist that you can use that would give you the ability to write your program in an orderly way and know that you've not missed anything. So we've got some pictures when we talk about batching applications. Here's one of them. And here is a system that we built at school, and this is one that you could build in your own lab. We use 80/20, and this was the first time that I'd been introduced to 80/20. And this was actually built by a capstone group. They built this and they put it together, and it was one of the best capstones that we've ever had. There are 3 liquid ingredients up here. There are 3 valves that allow the liquid to flow down and then come into the main mix tank. We call this the main mix tank here. Underneath the main mix tank, there's a load cell. And then as you mix the stuff up, then you let it drain out into what you'd call where we would actually send the stuff you're mixing here. So you're mixing 3 ingredients in this one, 3 liquid ingredients, and that would be a simple application. We've talked about, but we have not added any solid ingredients into this, but you would use an auger or something else to bring the solid ingredients into this as well. Here are some advertisement pictures from various manufacturers of other types of batching systems. This would be a solids batching system, and each of these ingredients, one by one, would be added into this main mix tank. This would be a solid number 1, solid number 2, solid number 3, solid number 4. And then they would be mixed in here, and then the result would be augered out down here. So this would be a simple 4-ingredient mixing system with the raw ingredients up here. This is a little bit different type of batching system. This includes a belt here that's not a weigh belt. These are weigh belts right here, and each of these are responsible for delivering a unit of a material onto this belt. So many pounds of this per minute, so many pounds of this per minute, so many pounds of this per minute, so many pounds of this per minute are allowed onto this belt. So what you're doing is you're making your belt your mixer, and you're basically layering these. So this would be the highest layer, the second highest, and so forth. This would be another way of putting your batch together. Now, argumentatively, this is looks to be a better system, but it usually is not as accurate because, first of all, you have dribble off of each of these, and you also have to phase these in so that this one starts, then this one starts, then this one starts, then this one starts. That's a hard thing to do. And also, this system can be built, however, with a lower height, because you don't have to put, here you have to put things up higher, and typically this gets to be a much taller system than this one does. So this is a headroom. This would be a shorter system that you wouldn't have to put as much height with, but it's still not quite as accurate. And this is considered typically the older type of system. This is considered the newer type of system. They're both typically a batching system. We're concentrating mostly on this one right here. Now you can talk about batching systems with this, but our code and our programming is typically using this kind of a batching system right here. Oh, what are we talking about here? Well, we're talking about recipes, and then we're talking about an active recipe in a program controller. Now, the storage of recipes can be in the program controller. It can be elsewhere as well. Your active recipe should be in the program controller, and the active step has to be in your program controller. The report is something that you would pick up by another computer and then pass along to that other computer. So the flow of data is you pick one of the recipes, then that recipe has steps. You go through the steps, step 1, step 2, step 3, step 4, step 5, and each of those steps has a number of words of control. We can talk about what those words mean. And then at the end, when you've executed that step, you have the actual data from that step that you want to report back to your computer system to be able to tell the people in the front office what you did. Was it accurate? Did you go out of bounds? Did you overreach? Did you underreach? What was the take on it? And also for inventory purposes, as you use raw ingredient stuff, you have to reorder those raw ingredients. So you want to know exactly how much you used in each of these steps of each of the raw ingredients, so you can add that up and make sure that you reorder that in a timely fashion. So that gets you started in the idea of how this is done. Historically, data has been stored in long strings of words, not necessarily in the format of an array. Today we have arrays in program controllers. So before we had arrays or the capability of arrays, we had to come up with a way to store information that you would consider from an array without actually having an array. So I'm going to talk about that, and we're also going to talk about how you build an array today. So the copy command is used for large table moves. In other words, I wanted to copy this whole recipe over to the active recipe. You probably use a command like this from Allen Bradley. The copy command took all 64 words and moved them at one time. You have to be careful because in the overall scheme of things, this might not execute quite as quickly as you want, and sometimes the copy commands had a done bit as well, so that you would not go forward until the done bit was active. You have to be careful. Okay, so you have to look at the execution time to see what would happen if the time extends beyond a reasonable scan time. Okay, so that would be a copy command. Blast of the whole from someplace in the storage of recipes into the active recipe. Now, There are different types of block of moves, and some of them are featured here, and we talk a little bit more about them. But the move block variant, move block uninterruptible, these are ones that are used by Siemens. So you have a little bit different names, but most of the time it's some kind of a move block. These descriptions talk about the same as we had for Allen Bradley, but with Siemens. So the move typically is with Allen Bradley is of a single word. With Siemens, it can be move of a single word. It can be move of multiple words with a move block. This move block variant, a variant is a variable that has, you can have any data type. So that's a little bit different. We'll talk a little bit more about variants later on in this chapter. But typically, you use a move, and this would be of a move block. Okay. So, description of the variant type is a description of how it's done. We also have, other than the idea of an array, we have the idea of a struct or a UDT. Now, a lot of data is handled today between manufacturers using UDTs. So we do need to know what a UDT is, but most of the time we use an array because of the time that it takes to execute a UDT. But you can use a UDT, and you just have to decide which way is the best way that you're going to go. So with a variant, you can, in particular, create generic standardized function blocks or functions for various data types. And we're going to talk about functions and function blocks in Chapter 14. But again, remember that variants can be used. It's something that I have had experience with myself, but you need to know that they exist. Here is an example of an earlier version of the Allen Bradley using the SLIC SLC processor. So here we're moving data from a location starting at file N10 word 10, and then N10 word 11, N10 word 12, and N10 word 13, based on an offset in this word called S:24. So the file that we actually are moving from starts at N1010, but then once we move the first 4 words, then the next time we come around and do this bit, we execute this bit. This would be a one-shot. We increment by 4, and this S:24 is offset by 4. So the next time we come through here, we would be moving from N10 word 14, word 15, word 16, word 17. We bump it again to 8. Now it would be N10, 18, 19, 20, and 21. And that gives us the ability to move multiple words and then increment and move multiple words again. So this is a way of doing that without having an array. These words here are, catch that. Now this is a typo. This should be in 731 and 732 and in 733. So we catch the 4 words and put them in the 4 words of the step. We don't use that anymore with the newer processors, but if you are using an SLC processor, you would see this pound sign, and that means you use that address with the offset that's in S:24. You say, well, is there any ability to have more than one indexer? No. With this processor, you only get one indexer. So we got this moving of these 4 words into this one clump of 4 words. And again, you can keep moving the first step, second step, third step, and then you use those 4 words in your actual programming. This is a move instruction with Siemens. Here is what would you do in a step. Now, this is sort of a crude state diagram from Chapter 11, but it shows you some of the things that you would need to do in the actual moving of a step. So the steps of a batching system would look something like this. First of all, you would look at the scale and see if it was stable, not moving, and then you would start adding the weight. Then you'd let the material flow into the tank and reach the preset, or slightly before the preset, and you would turn the valve off, or the feed element off. Then you would let it settle for a little bit, and then you would let your weighment be recorded, and then you would check to see if there's any other thing you need to do in that step. First of all, you would say if there's an agitation that needs to be done, do you have any heating that needs to be done, anything else that needs to be done in order to facilitate that step. Sometimes you would also ask, should there be another fill? Should you get a secondary fill or something like that as well? If you have multiple premixes and that type of thing, you might want to add that as well in there. But in order to add a step, you need, the basic idea of a step is get the material in and get it recorded as to how much you actually added. Everything else is basically added on to that step. So also at the end of the step, do you need to dump the material from that weigh vessel to someplace else? And if it is, then you need to go through some process, maybe, that says I need to flush and clean out my tank or clean out my pipes and then go forward. So all that has to be considered when you're writing the logic for a simple step of adding an ingredient. So all that information is contained in those words in that array. So in those 4 words that we showed you before, that would all have all this information in. Maybe it'd be 6 words, maybe it'd be 8 words, maybe it'd be 10 words. You may want to add more information, and that would all expand your array. But that's how it's done. Pretty much traditionally the way it's been done. At the end of this weighment, you want to record your data and save that information into some kind of a database. And the old one for Allen Bradley is RSSQL, and that's commonly called Rascal. We've moved on from that today, but that's the typical one that they used for many years, was a database program called Rascal. Now we go on to how do you create an array? So up until now, we just talked about a number of words, but now in order to do this, in order to index through, both Siemens and Allen Bradley require an array in order to do that today. In olden days, they just used an instruction that basically cycled through a sequence of words in a data block, but now we actually have to create an array. With Siemens, you actually have to create a data block. And this data block is when you're adding a new block, you click add a new block and then create a data block. And that gives you that's not the name of the array. The array is stored in a data block. But in the data block, you actually give a name to that, and I call that array in the data block. So it's data block 1, and then the word is array, and then you can assign how many words that you want, and it is of a specific type. Like you want to save integers, double integers, floating point, that type of thing. You can save based on what type that you want. And then you reference them in your main program, OB1 or wherever, but you reference them from this data block. Allen Bradley uses under, instead of main program, it's parameters and local tags, that choice, and then you click on a name, or you create a name, and then under that you create the type, an int or whatever, and And then under that, it gives you some choices down here. So the array dimensions. So if you want to give it a dimension of 1, it's a single word. If you give it multiple words, it becomes an array. So dimension 0 is the first dimension. Dimension 1 would be the second dimension. Dimension 2 would be the third dimension. So you can have a 3-dimensional array if you want to with Allen Bradley. You can't do that with Siemens, but you can do that with Allen Bradley. So under the Edit Tags tab, you can create a name, which is the same place that you create all your variables, but this becomes just another variable in your main data area under your tags. When you address it, you can address a word, an array by a number, or you can actually use the dot function to peel away and get into a bit in a word. So this would be, in this word here, I can address any word in it by this table 1 index 1, but I can also use the dot and index a bit in the word and get me up to identify any bit in that word. So I can pick off a bit in a 32-bit word by using the dot format and being able to do that. Okay, very rarely used, but you can do it. So here is a move block where I add a number in table 1.index1 to table.index2. So I could add like word 0 to word 1. Excuse me, I could add 1 to this word and then put it into another index down in the same table. So I can take, if my index was 0, I could say, okay, take the number here in 0 and add 1 to it, and then take the result and put it in. Maybe if index 2 was 1, I could say add 1 to this number and put it here. It's your choice, but you can see how this can be used in indexing words. You can also use the for next loop, which gives you the ability to do looping in your main routine or in a subroutine. And this gives you the ability to iteratively go through and do something a number of times in ladder logic. You can also write this in SCL language, which is the procedural language. You can do it as well there, and probably should, but you can do it in the ladder if you want to. So you can write a for next loop in Allen Bradley. UDTs stand for User Defined Table, and basically these are a way of storing, instead of an array, storing variables in a field like with a database. So if you had different types, in other words, you had a name, which would be a text, and then you would have some integer values and some floating point values, maybe some Boolean values. You could store those all in a field, and that would be a UDT. Typically, UDTs are the way that one vendor passes information to another vendor in the passing of information systems and program controllers and that type of thing. So if you had a program controller that was making a product, making some pieces for an automotive vehicle for that type of thing, and as it was making them, it would pass that information off to the user of that information in the format of a UDT. And this is how it would be built. And it looks very similar to an Access database. And you can see that this is sort of a using of the database concept, but in a program controller. And Allen Bradley and Siemens both use UDTs. Circular tables are a way of storing recipe information. And this concept is one that is very powerful, because what if this downstream computer or the downstream system is not locked step with your process and it gets a little behind? And let's say that it gets behind by 2 or 3 counts, and you don't want to lose those 2 or 3. You want to keep them all have access and see that that information is passed to the downstream system. So what you do is you use a thing called a circular table. And what the circular table does is it stores the first step, then it stores the second step, then it stores the third step, then it'll store the next step that's empty. But if the system that's downstream comes in, it can come back and take all three of these and start over again. But it gives you a little bit of time. The downstream system can get multiples of these. And let's say it stores this one and then starts back over at the top with the next. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It gives you a time duration of 4 steps before it has to come back and pick up another one. So actually, this downstream system can be a little bit delayed, but still actively get all the information. It doesn't have to be right there all the time. It can be a little bit delayed, and that gives you a little bit of a buffer. Some people would call this a buffer between the two systems. But this is what's commonly used in order to get data from one system to another. Okay, from the Easy Book. The Easy Book is the Siemens introductory book, and they've had several versions of it, but they keep updating it. But they do talk about in the Easy Book about data logging, and it's something that we ought to look at because everybody does it. How they do it is different, but this is how Siemens does data logging. It's stored in a CSV, comma separated variable format. The data records are organized in a circular log file. That's the circular table of a predetermined size. So basically they do this circular table and they store their variables in CSV format. Now here are their instructions. Data log write, DB, data log create, database, data log new file. All these are used for getting that data into that data log. Open and close are 2 more that they have. These are just for you to review, and you can take your time with looking at them. And this is something from the Easy Book, but you should at least be aware of the fact that the Easy Book from Siemens does take the time to talk about the idea of data logging, which is the idea of getting the data from your step information and taking it to the next computer in line. And this is how they do it. So now we're going to go back and look at some of the older addressing schemes and understand a little bit about why we've moved on from these addressing schemes. But this is something that was done in the 80s and 90s to address arrays, but not necessarily using an array. So this is called indirect addressing, and the example here is using a bracket. So whatever was in the bracket, the reference in the bracket, the number that's in that location replaces whatever the bracket says. So basically, if I had B3/ let's say N7:0, the contents of N7:0 is a number, and that number would replace to everything in the bracket. Here's a case, N7:0, B3/N7:0. If N7:0 was 0, it would be, this instruction would be a 0. If N7:0 had a 1, the reference would be B3/1. So the brackets say everything in here replace with what's inside this data location, called indirect addressing. Very powerful way to address things, but it has some flaws, and I'll talk about those in a minute. So here's some examples of that. Again, this has gone away. It's not being used anymore. Here's the flaw. It's hard to debug or troubleshoot if you're not the original programmer. So don't use it unless you find no alternative means to program the task at hand. This was what was supported in RSLogic 500 and RSLogic 50. In other words, RSLogic 5, excuse me. RSLogic 5 programmed the PLC 5 and the RS-Logic 500 program the SLC program controllers. So you can, or RS-Logic, RS-Logic 500 program the SLC program controllers. So you can use this in both of those languages, in both of those processors. But both those processors we've moved on from those, and we moved on to RS-Logic 5000 with a control logic processor, which does not use that indirect addressing. They moved on. Indexed addressing was found as well in the SLC and the PLC5 processors, and it has this pound sign in front of it. And we talked a little bit about the pound sign before, and here it is. So when you see the pound sign, you say, okay, it's not necessarily just this address, but this address offset by the number in S:24, and you only have one S:24 in your program controller, but basically you only had one indexer. But this says move that information from N710 offset by the number in S:24 to the location in N750 offset by the number in S:24. The pound sign says move it based on the offset, so that gives you your indirect addressing. Okay. So from this, you can actually build table to register, register to table, and table to table. And you can do that. Here is the table to register. In this case, you would have the pound sign in the first location. Here is the opposite, where you'd have register to table, and here you have the pound sign in the second location. And here you would have an example, and you would put this in a for next loop, and then you would just keep moving it down, and that would give you a table to table. Okay, not used a lot anymore. So here's some of the things, the strange things you can do with this indexed and indirect addressing. You can do all kinds of strange things. You can double up on it, you can have one within another and all that kind of stuff. And we don't get into this too much, but this is something that you can look at if you are looking at the old programs. This gives you a little bit of a heads up on what they're doing. So here's a table-to-table move from Siemens and Allen Bradley. Old style. This would be the same thing with the Siemens. This would be the same thing with Allen Bradley. Table to register. Old style with index addressing. Siemens and Allen Bradley. This is the register to table move. Old style. Siemens, Allen Bradley. Now we're going to break off from the programming a little bit, and we're going to talk about scale systems. So you can, how do you get the number from the weight into the program controller? It's a good question. You need some kind of an interface, and typically interface is provided by the manufacturer. For, in this case, it's Siemens. Siemens has this Cywarex WP231. We bought some of these. They're not cheap, but we bought some of these, and they go right on the front end of the 1200 processor, and that's what we used for that weighing system that I showed you up at the beginning. And it gives you an accurate weight, and it's very quick, and it gives you a response time that's very, 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 very quick. And you can use this and know that you're getting the weight in very accurately. They have other things that you need with this. You could have a separate scale readout for just the scale. You can have what they call a Cywa tool, and that gives you the ability to set up the Cywarex WP231 with a computerized system here. And you also have to have the connection to the load cells. So this takes the information directly from the load cells and brings it in, and then it records, it brings it over to the processor and tells you the actual weight. You also have the ability to put your HMI on the PLC, so that gives you the ability to do that very quickly. So I've not explored the SIWRX very closely. We just used the one example. We did it the one capstone group that did. They're really the two capstone groups that did that. So we're not as attuned to the SIWRX capabilities, but it's there. Now, this is an example of a load cell. Load cells are not cheap. This one is about $700, but they're very accurate, and they can give you a very accurate reading of weight. What they are is if you stretch them or you put them under tension, they actually stretch the resistance and makes the little resistance go a little bit higher because you stretched it a little bit. So that's what this is. It's a resistive device, and it's very accurate, very high accuracy with these things. Usually you place them under the four corners of the weigh cell or the weigh equipment that you're going to have. Sometimes people get away with three, but 3 or 4, they put usually 4 under there. Now here's an example of a strange one. This is not your average weigh system. This is one where you're actually weighing something that's moving down this conveyor belt live. In other words, as it's moving by, the weight is being recorded. These can be very accurate systems. They're not as accurate as the one where you're actually just dumping it in and weighing it in a still system, because here you got movement and you're having to filter that weight, that movement out of your system as you're watching the material move by. This is not quite as accurate as the one where you're just weighing directly into a weigh vessel, but this is used, and people do use these systems a lot. Here's a picture of the weigh cells on a tank. And here again, we're weighing material into this tank, and then we're making a batch of something from that. So we're weighing in and doing that. Okay, so the rules are that this up here does not touch this tank. There's no way that you're putting tension on this tank from fixed equipment. So you're basically letting this tank float, and then you're taking the material out the bottom. This is a cheaper system than the SIWRX, but it's not totally cheap because it's about $300. But the problem with this one is you have to be, this is an analog, you bring the load cell in and it takes you the analog out. But the analog out only updates every three times a second, which is not very many times in a second to be able to guarantee that you're getting a proper weight. However, with this system, you are forced to write usually some kind of a predictive program called an interpolation program that interpolates and figures out the weight and the rate of change of the weight from each point where it records this. So this would be every third of a second you get a new weighment, and you would have to write a program calculating that difference. So you have to decide as an engineer how best to attack the program. If you want an update every scan, you might want to pick the SIWRX or the Allen Bradley equivalent. But if you want to cheapen it and you got a lot of systems, you may want to use something like this. But here you're going to have to write this little program that does this linear interpolation. If you want to do that, you can, but it takes time, and time is money. So you have to decide which way you're going to go. Okay, so now you have the ability to look at steps and look at weighments, and now you've got a little bit of an idea of what a scale system does and what it brings to the party. But how would you set up a batching system? That's a good question, because when you first start out, you don't know the questions to ask. So this chapter is multifaceted, and one of the things about this chapter is it asks you a question: what do you get from the various types of specifications that are out there? Well, this is one that is very good, and I just put little pieces from it. I cut some little pieces from it to show you that the accuracy that it has and some of the things that it can do. But this is an ISA 88, International Society of Automation, SP 88, specification number 88 that they did back in the 80s. This is old, it's not new. But basically, this gives you a structure for a batching system. And some of the experts in batching systems got together and put this together, and they did a very good job. And maybe you don't need all this, but it does give you a checklist from which you can ask questions that then you can decide, do I need this or not need this? What about this? What about that? And it gives you some things to ask, good questions to ask as you're designing a system. Here's one of the defined in the specification, the different types of modes. So you can have auto, you can have semi-auto, you can have manual, you can have a bypass mode. I don't know what the controlled mode is. You can reset, you can have alarms or alarm acknowledged. All these kind of things you should consider when you're putting the program together. Here are different types of feed types: filling, dosing, formulation, blending, and batching. I don't know what all those mean, but at least you give some ideas that you might want to ask about to give you some ideas. Types of feeds: gain in weight, loss in weight, flow meter, dump to empty, hand add. In other words, you could have a hand add in there as well. And here's the steps just in going through the writing of the program for the step. Pre-feed, feed start, feed stop, feed finished, feed post-feed. In other words, all these need to be considered as you're trying to come up with a good plan on how to write your program. And guess what? What are these? State diagrams. They have a multitude of state diagrams, much more complicated and much more involved than the one that I put up at the very top of of this chapter. But they do a very good job in reminding you of all the things you can possibly think of in a state diagram for a batching system. And they have them. They're there. Reporting. What kind of reports do you have? What are they about? And terminology. What do these terms mean? So if you have one main mix tank, batching system is pretty straightforward. And all you have to do is go step by step by step by step by step, done. Step 1, active, then done. Step 2, active, then done. Step 3, active, then done. Step 4, active, then done. Step 5, active, then done. So that's typically of how this is executed. How do you program something like this? You say, there's nothing like this in the real world. Oh, yes, there are. There's programs like this all over, and I was a part of this, working with programs like this. Not the exact one like this, but many like this. So in this situation, you had 3 main mix tanks, A, B, and C, any of which could be running at any time. So you could have a mix running in A, another mix running in B, and another mix running in C, all different recipes. Any main mix tank could call up pre-mix tanks to be used to be making premixes, as well as something being added to the main mix at the same time. In other words, I can be having something in the premix tank as well as something in the main mix tank. And each main mix tank can call up any of the premix tanks in order to start making a batch for its main mix tank. So main mix tank A could call up premix tank A and B. Main mix tank B could call up C and D. Main mix tank C could call up premix tank E and F. Or let's say that one of them was already busy with something. Tank A could call up C and maybe E. It could call up any of the ones that are available and start making premixes for it. Or you can make 3. You'd have 3 premixes going with the same one at the same time. It's your choice how do you want to write the program. So we've been talking about recipes from filling of a tank. There are a lot of other types of recipes, and I'm just going to go through a few of them, and I'll remind you that there's many more than what I'm putting down here. One was a program that I wrote a number of years ago called a valve nest, and there was a number of ways that you could transfer liquid through this valve nest, but some of them had to be preemptive. In other words, you could not move certain liquids through certain valves because of contamination. So you had paths. This would be much like a telephone connecting system that would actually, you would patch cord in a path through the valves or through the switches so that you could actually get a telephone system to work. Another one was a heat soak cycle of a steel reheat furnace. In this case, certain types of steel could be used with other types of steel, but they couldn't be used in other areas because of certain conditions. In other words, you would have how long this piece of steel was in there and at what temperature it was, how long it was going to soak, and what would be the ramping up and the ramping down stages of it. So you would have all that information going at the same time. Much similar to baking a cake. So if I had two different types of cakes, one would be a certain type, and another would be a certain type, certain size. Can you put them both in the oven at the same time? And many times somebody would have to sit there and figure this all out. If you want to do this automatically, well, that would be something that you would say that would be the same as a steel reheat furnace situation. Here are some of the Siemens data logging instructions and batching instructions that they have. Now, this is just taking the information off of the TIA portal and showing some of the stuff that's there. So recipe export, recipe import, data logging. There's those they have, the choices they have, and under those, some of these other examples right here. Okay. Something that's interesting, and I put it in here as well, was this idea of saving of information so that you would have it for as a constant. And when you're in the run mode, they have this word called snapshot, and it copies a value, and prior to uploading, this saves your data recently uploaded. It's a nice technique to know. So you can take a snapshot of something and then save it, and that gets you the information that you need for later use. Also, both Allen Bradley and Siemens have batching control systems that they sell, and this is the one from, showing a little bit about the one from Siemens. Not that you're going to be baking cakes, but it shows you a little bit about what they do. Also in Chapter 31, I did a project for a group, and it's in Chapter 31 of the lab textbook, and it describes a robotic arm that was programmed to pick up and place a checker in a box. The robotic arm consists of 4 axes and a suction attachment. The entire program was written in a week and used to capture on group's display. The program is written entirely with storage array of the positions of the robotic arm, and the whole program is given in its entirety in Chapter 31 of that text. So I would give you this because this does talk about the use of stepping through arrays, which is very similar to the idea of recipes and batching systems. It uses an array for each of these axes, and it steps through and gives you up to 10 positions for a set of moves, and then you decide which ones you're going to use. Basically, it gives you the ability to handle arrays and move through arrays, and then be able to use that to move these axes on this robot. Chapter 31. And this is, again, from the text programming guide for S7, 1200, 1500, revised version for bringing up to speed anything after version 2014 of the TIA software. So the language for Siemens especially is not static, it is on the move, and it is something that you need to look at. And this text, this book here, I just took a few pages out of it to give you some ideas of some of the stuff that's moving, that's moving in that regard. So again, it talks about the idea of the variant type, the move block variant, which we talked about before. It also talks about the idea of serialize and deserialize. Now, I have not done this personally, but if you have a data record that you want to move, many of the times take it from an array and send it to a device, you have to serialize it, and that's something that you might or might not have to do. In the iDevice, you have this idea of being able to transmit information from one program controller to another using the iDevice transfer method, and this serialize and deserialize is recommended as the way of doing that. Okay, I've not done this personally, but again, it's recommended that you read through this in order to figure out how to do it. And variant, some variant instructions, variant get, variant put, and some of those instructions you might be interested in looking at. And here's some instructions that are only used in this SCL language, which is a procedure language. Variant to database, variant any to variant, or database any to variant. So you can go from a database to a variant, or from a variant to a database. And this talks about the runtime instruction measures the runtime of an entire program, individual blocks or command sequence. You can call this instruction in ladder, FBD, SCL, and STL. Okay, so again, if you want to know how long a program is taking to execute, use the runtime instruction, it'll tell you. And comparison of tags. This is again in version 14 or higher. So it gives you the idea of being able to compare different types of tags. Moving through this rather quickly because I just believe you can spend some time on this if you want to, but just bringing up some of the stuff that is new. Here is the ability to comment in ladder, and it's a new way of doing that. You can, for commenting in ladder, it gives you the ability to show the comment fields separately. Very interesting way of doing it, called a block comment, or a network comment. This one's, I guess this one's the comment on instructions. Sorry about that. This is the comment on instructions. So here is the block comment. Here's a network title comment. Here's a network comment. And then here is the comment on instructions right there. This is a very powerful, very useful way of giving more information so that somebody can look at the program and figure it out. Very powerful way of doing that. You can also put in comment lines in your watch tables. So this gives you the ability to put information into your watch table so you can have comments there as well. And system constants. You can have system constants that can be brought in and used. This talks a little bit about those. Saving them. User constants, saving the user constants. So it gives you some ideas on constants. So this is some stuff that you might want to look at from that data book. Okay, so here's some of the things that we've talked about in this chapter. And here are some of the places that you can go for some of the labs that we have. Chapter 12, Chapter 13 of the complementary book, the lab text. Chapter 14 is the batching system program, and Chapter 31 is a simple robot. Here is the Simon Says program, and I'm going to talk through that just a little bit. So one of the things you're asked to do is to look at this program and take it and transfer it over to something that you can write in Siemens or Allen Bradley, and I'm going to do that right now for you. This is the Simon Says game. It's found on page 59 of chapter 13, and basically this game, while old, it still shows this principle of indexing through a table. So we have a stored table of lights, and we go through 15 different lights, and if you go through all 15, if you remember the sequence, you win the game. So the way that the game was written by me, originally I did 3 lights and 3 buttons instead of 4, but you're to put the 4th one in. And here's the beginning of this program. As you look at it, this is written in for the SLC processor, and it has the index addressing. So this has index addressing. It uses S:24 as the pointer, and if you have a move instruction with a pound sign in front of the number, that means that number with the offset of S:24 is where you're actually going to move the data from or to. In this case, we're going to look at the actual information here, and we're going to say, how would you start writing this? Well, since this is the older Allen Bradley, they use this SOSR instruction. So the actual one shot is B3:0/1. Now that is word 0 bit 1. So we're going to have to adapt that, and that's just going to be our, let's just call it B3:0_1. But we're really not even going to have to use that, because we can ignore that first line. We can go down to the second line, and we can just say use the input. If you're writing in Siemens, you can write the positive transition of the I of the input for the start button. This would be my start button. And you would use that input with a memory bit as your blocking bit, and then you would come down here and you would have a seal on that. But now I'm working on rung 1, not rung 0, and then I have these 2 normally closed that we don't really know what they are yet, but let's just call this coil B3:0_2, and then we would use that B3:0_2 down here. Now, what does B3:0_2 mean? Well, it really is the run bit. So we're running the game. Okay, so then we come down here, and then we come to rung 2, and we notice again, this is a one shot off of it says the game is starting. So B3:0/6 is the game is, excuse me, this is the actual starting here of it. That basically says that we are this basically right here says that we're running. Okay, now this bit right here is it is used to clear the this B3:0/6 is used to clear the this coil here if we need to. So basically, when we're doing the run, we have a bit here that does a clear. So B3:0/6, which is a clear bit, is this is running B3:0/2. And use that as a memory bit, and that says to run, or that is to reset B3:0/6. It's a reset bit. This is another memory bit down here. So that's how you would handle rung 2. Rung 3 is it comes from B30/7, and then it has all these other seals and stuff like that in it. So I'm going to let you go down through here, and with this technique of working with this, instead of slashes and all that kind of stuff, put B3 and then underscore, and that'll get you started. But the only other thing that's going to be interesting for you here is that this S:24, which is in rung 7, for that one, we're going to have the B3 0_11 or B3 underscore underscore 13, and it's going to go to a clear or move a zero into the word index. And then when we come down, this word index is an integer. And we're going to come down here in a little bit, and we're going to look at it, and we're going to see what actually is going on with this. Okay. Now, on the second page, we have some things that are going on. So when the done bit of this timer comes on, we add 1 to S:24. So when we do that timer, whatever that bit is, we call that a done bit or .q bit or whatever. And then we do an add of an index, the word index, plus 1, going back to the word index. So we increment our indexer by 1. Here, we're doing a move, B30/2, B30_2. We're doing a move. And here's where it gets interesting, because we're doing a move of our array. Now we have to have an array someplace, and I'm going to talk about that in a second. Parent index into a fixed word. So let's just call it fixed word right now. Okay. Now what we're doing is we're taking from an array of words and we're moving it into a fixed word, and we're going to do our logic out of it. So if index is 0, we're going to move this word in. If it's 1, we're going to move this word in. 2, 3, 4, 5, 6, etc., etc., etc. We're going to be moving into this fixed word. Okay, now this fixed word, which was called N720 in this program, you just use the word fixed, and then as you are addressing the bits in it, see what they're doing here is they're saying, okay, N70 or the word fixed dot X0 would be the bit for N720/0. These are equated. So if you see dot N720 dot or /1, that would be fixed dot X1, etc., etc., etc. So you're basically pulling bits out of this word that you've moved from this table, and then you're using it to describe some logic, and that's what this is doing right here. And that gets you pretty much through this program. If you can take this program and to do that conversion and try it out, you can pretty well get your program to run. All I'm asking you to do is to add a fourth instead of just having three. Add 4 lights, 4 push buttons, and do that. You also have to configure your array with 1s, 2, 4, or 8. So each word of these has to be a 1, a 2, a 4, or an 8. And you can do them in any order. They don't have to go 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. You can do 1, 2, 8, 4, whatever. What that's doing is it's putting a 1 in one of these bits. You're either putting a 1 here, a 1 here, a 1 here, or a 1 here. One of those 4 bits is where you're going to be picking that information up. And that should get you through that pretty well, okay? So here's this table. As you notice, it's been filled in. And you would do that same thing with a watch table or a data table for Allen Bradley. Away you go. This is showing how to build an array. And fill in the words. And here we don't use a whole word, we use just a byte for the array because we only have to use 8 bits. We don't have to use 16 bits. We can just use 8 bits because we only have but 4. And then this would be the actual where we would do the moving of the data. So it shows you exactly how to set that up. And the same with Allen Bradley. Okay. With Allen Bradley, you can use the exact same logic as was done with the start because there's one shots are a little different, but you can do that. So this is the whack-a-mole game. Notice that we don't give it to you as a written program, but you can do the basic same thing with it as you do with the whack-a-mole or with Simon Says. So here you've got 4 buttons, or you got 4 lights and buttons, and they're basically what you have is you have a table of which button. So you go 4 bits, and you got one of these on, and you then put that into that fixed word, and then you go to the next word, do the same thing, and the next word, do the same thing, next word, do the same thing. So you're taking one at a time, and then putting it on, and then letting the person push it within a certain period of time, like a half a second. If it's a timing diagram, you would give them maybe a half a second to push the button before the light went out. So instead of whacking the mole, you would actually be pushing the button. But also in this one, we're having a second table that you would move through that would be your presets. These would be your preset times. So these preset times are this time right here. So there's a preset time between you turn one on and when you do the next one. And you can vary that as well. So the first one would be right here, the second one would be right here, the third one would be right here, the fourth one would be right here, etc. And you pull those out and you put those in as well. Now, what's the difference between this program and the Simon Says program? The Simon Says program goes 1, then 1, 2, then 1, 2, 3, then 1, 2, 3, 4, then 1, 2, 3, 4, 5, etc. until you get to the end. With this program, all you're doing is you're going through it one time. You don't go back and go through it again and again and again. So that's the main difference between the two programs. But this is a pretty straightforward program, and you can easily write this one as well, either with Allen Bradley or Siemens or both. So also, if you want to write it with a UDT output table, you certainly can. So this shows you the basic different philosophies between the two games to give you a little bit of a picture of how the program is set up. which is what I just said, just the differences are. So basically that's it. And this is a liquid batching system, which we have a video of that would show you a little bit about how this is set up. It's a fairly interesting lab. It was set up originally by a capstone group, and we have a video here that's coming up in a little bit that shows you how this is done. And the key here is there is a programmable controller and there is a load cell. And basically you have to get the weight from the load cell, and as you add weight to this mix tank down here, this main tank, then you go to a certain weight and shut it off. Then you go to the next weight and shut it off, and you go to the next weight and shut it off. And if you had a stirrer in here, you could actually stir it all up, and then you can drain it out, and you could have a mixed batch of whatever you're making. So that's a liquid batching system. Okay. Talk a little bit about some of the stuff that we have here. We do have this Soarix WP231 card that goes on to the Siemens processor. It's a special card. There's the load cell. Or you could do as the one group did and go through a load cell converter. And this is a load cell to analog converter panel, and it turns a load cell into an analog signal, and you can do that one as well. So we're getting down through this pretty good. And this other one is the robotic arm, and we talked about it a little bit earlier, but basically this one is an array handling program. It's in Chapter 31, and it's very powerful, and it gives you a good experience with arrays. So if you want to go to Chapter 31 of the lab text, it goes through this whole program and shows it to you in its entirety. You can type it in, try it out, and move a robot. Here are the exercises in this chapter. So here are here's a list of a table of some values in some files, N7 file and N10 file, and then here are some questions based on those values. So here I have a pound sign on the N7 0 or on the N7 file, and I have a no pound sign on the N10. So that means I move the value at N7 0 offset by the value in S:24, which is 2. So I say N7 0 plus 2 is N7 2, which is 210. And I move that value over to the value of N10 0. So after this one is done, the value here in N10 0 is 210. So N10 0 is equal to 210. That's the answer to this question right here. So that's the only value that changes. Here we have a pound sign, and we have another pound sign. So it's N7 0 offset by 4, or N7 4, which is 542, going to N10 0 offset by 4, or N10 4. So 542 N10 4 is equal to 542 at the end of this problem. So the next one, we have a pound sign on the destination. So N7 0, which is the value 102, goes to the value N10 0 plus 3, or N10 3. So N10 3, after executing this instruction, will equal 102. That gives you some experience practicing with these index addressing. And I believe you can do number 5, 6, 7, and you can do those. So basically we're down here to these problems now. Here we got a question about review a scale input method and comment on the interface between the scale system and the PLC. And I've talked to you about that before with the linear interpolation. Certainly it's possible to do linear interpolation if you need to. The only problem with that is it's a program you have to write. And well, welcome. We're looking at a batching system at the University of Toledo. This is a capstone group that made this, and we're going to show you the parts and pieces of this system. And first of all, there is a program controller on the back there. We're not going to go all the way around and show it to you exactly, but there it is, and it's got a Siemens processor, and it's also got the weigh scale interface to it, and that then is wired to a load cell down here that we're looking at, and the load cell is right here. You can see it, and then we go to up here. There's 3 water valves that control the flow of water from these tanks up here, and then we have a flow valve that controls the drain that goes down to the bucket underneath. So we're looking at a process here that we were going to mix some various ingredients together, and we're going to look at the process of doing this, and we're going to look at the program, we're going to look at the HMI part of it, and we're going to turn this over to the head of this project. Her name is Sarah Weber, and we're going to introduce her now, and she will be able to discuss the rest of the project. So here's Sarah.
Hello.
And she's going to talk about it and discuss the process. Okay,
so an operator can either redefine these set points that are currently on the HMI or keep them. We can adjust them just slightly, which I will do really quick. You select the recipe, go to active recipe screen. That will show the set points of that recipe. Select start recipe, and the system is running. The HMI also allows the operator to view the live weight of the tank along with the present values distributed by each of the tanks, which will update on the HMI. So the tank 3 was empty, so this batch didn't completely run its course, but and now that it's complete, it'll show on the HMI screen of the mixed tank level and the preset values that were selected from the set points. And to drain the mixed tank, it has to be done through manual. So manual has to be turned on, and you start it to drain. So to show everyone the code and the program here on an OB1, in order for to operate and to report the value of the load cell from the scale module, a value of 230 must be moved into the command B, which is part of the cyclic interrupt. So this occurs, and then this weight is converted to an int value, just to make it a little easier to work with. From there, this OB1 is really kept as a control screen. There's the stop, start in different modes, manual or auto. Manual mode, there's a function block was utilized to write that function, and that's really organizational purposes, so it's not overwhelming. In OB1, right now you're looking at manual mode program. The recipe function, here the values are moved, the start values moved into a UDT array, and the valves are set at certain points. Well, once that value, in this case, is greater than or equal to the set point value, it will reset this valve 1 and set the next valve. And there's additional logic to observe these values on the HMI. So this here would just essentially shut off this valve and move this value to this tag. A UDT was used here to show you. It was created under the data types. An array of ints was created within that, and to utilize that UDT, a data block was created, and each tank here holds this whole tank weight array along with the recipes. So the recipe, really, this array is a little big for this program, and this wasn't really utilized as far as the rest of this, because we really utilize these first three places to move the values into that recipe. So and then further down, I'm sorry, the way it's written to allow the operator and the HMI panel to set their values is a simple moving that HMI sent point to the recipe array. And you see this in this rung here. Actually, these last two rungs is how that's accomplished.